Is the presentation visible?
Yes, sir.
Okay. Good morning, friends. We have discussed in the last module the basics of denotational semantics. A, a formal way of doing semantics in terms of lambda calculus, in terms of mathematical functions. And we have recognized that to be able to express the semantics, we need a number of predefined semantic algebra domains, which is known. And in terms of those domains, their operations and so on, we can express the semantics of a program of a lambda calculus expression in a very formal terms. And with that introduction of semantic algebra of various kinds, including builders like product and sum and all that, arrays, we have done two simple examples, computational examples. One that was of binary numerals, notational semantics for binary numerals, and then a little more complex example of a calculator, where we allowed a single value memory, single value store, where any value that is computed is by default kept in the store and can be used subsequently, and that is erased when the next value is again computed. So that was more like rudimentary examples. Now we take this forward for proper programming languages, proper in the sense that programming languages with which we are more familiar with, and those are mostly called imperative languages. Let us see what. So this module will talk at length with the typical languages that we are familiar with, the languages which has different kinds of numerical and Boolean expressions. It has assignment, it has conditional expressions, and so on. And it can do, say, file operations. It can have dynamic typing. It can have recursion, and so on and so forth. So slowly we will develop this and show that a typical imperative language can be expressed, the semantics of the typical imperative language can be expressed in the denotational form in a very formal and constructive way. Now, so this is roughly what we'll cover. It will take a couple of classes for the discussion. So what is an imperative language? I mean, let me give that semantics first. So as we know, most sequential programming languages, of course, I mean, I must tell you here that we'll be dealing only with sequential programming languages here, not with concurrency or parallelism in that way. Now, let's say the most sequential programming languages, in those languages, what we do is we use a data structure, right? That is what you learned from your first PDS course itself. The data structure exists independent of the program, and it is not explicitly mentioned in the language's syntax, right? Don't consider cases of Python where you have data structure as a part of the language. It can be viewed differently also, but for most say C, C++, Java, these languages, the data structure is not a part of the language's syntax, but it is possible to build phrases that access it and update it. Like stack is a data structure. I can build a phrase to push an element in the stack or check the top of the stack and so on. I can update it by push, pop, etc. Right? So a data structure is an inherent requirement of a programming language. So this data structure is what is called a store, because it is something which has to exist and keep on changing state as we go ahead with the execution of the program. So languages that utilize stores are called imperative. Right? So that's a simple way to look at it. So fundamental stores, as you know, the store could be a primary memory, which is what we will try to model initially, or it could be a file store, which is persistent beyond a single execution of your program, or it could be databases, which so it we do not differentiate immediately between these types of stores. We just consider that there is a store that can keep the data structure as the program executes. So the store and the program share an intimate relationship that we know. We know. We are just trying to formalize this in terms of our notions in the semantics. So a store is critical to the evaluation of a phrase in the program. Now, here is what we know, but in a little different view. A phrase is understood in terms of how it handles the store. And the absence of a proper store makes the phrase non-executable. So if I'm trying to do a program to, say, reverse a string, I need a store which I perceive as a stack, as a data structure. So the program will have to handle that stack. It has to push elements. It has to check if it is empty. It has to pop elements, keep on doing that till it gets empty and so on. And in the absence of this stack, the phrases or this push pop, this kind of operations or the program is non-executable, right? So a phrase is just like that. So what does the store do? It serves as a means of communication between different phases in the program, right? Somewhere I'm doing a push, later I'm doing a pop, I'm checking if the stack is empty. So the value computed by one phrase is deposited in the store. So you have done a push. So that another phrase, say when I do top or pop, that can use them. And the language typically has a sequencing mechanism that establish the order of this communication. Naturally, when I do bring the reverse of string, I need to do the push of the elements in a certain sequencing order. And once I'm done with that, then I do the pop of the elements in a certain sequencing order. And this whole sequencing actually establishes the order in which the communication is happening between the program and the store, right? Store is inherently a large argument. That's what we understand. And only one copy of store exists at any point during the evaluation. These are all facts that we know, but we are trying to look at them from a mathematical formulative framework. Right? So we use lifted domains to model store. We'll see why we need lifted domains. Okay. So let's say we have assignments, an example language which has assignment. And in that, let us now introduce something called a command. Command is a phrase that I'll typically execute at any point. So it's kind of, the syntax is kind of a Pascal subset, which does not require declarations and all that. We are not going into those details. And a program in this language is a sequence of commands. Let's say the store belongs to a semantic domain store written in italicized manner and serve as argument to the valuation function. So I have a valuation function C for the program or the command, which is command mapping to lifted store, mapping to lifted store, which means that C takes a command and the present state of the store, applies the command on the store, or kind of executes the command based on the current state of the store and produces a new store from that argument. So it is kind of, every command is a transformation from the current state of the store to the next state of the store, current state of the data structure to the next state of the data structure, right? Now, it is possible that a command might not terminate its action upon the store. It can keep on looping. I can have an infinite loop. I can have an infinite recursion and so on, right? So it is possible that when I try to apply a command on the store, then it does not terminate, right? So it does not produce any store as a result, which it should. So what is our modeling for that? Our modeling for that is bottom, which is no result, non-termination. And therefore, how do we plug that in to our semantic domain? We lift the semantic domain. So store is lifted to store bottom, the lifted store, which you know is everything that store has, union the bottom element to be mapped when a computation does not terminate on a given store. Now, there is an inherent sequencing in the language. It's a sequence of commands. So sequencing is marked by writing one command after another, separated by a semicolon. Right? That's typical of Pascal. It's typical of C, C++, etc. also. So when we do that, what is our interpretation? Our interpretation is we first execute C1 on the current state of the store, produce a new store, and then we execute C2 on the current on the transformed store produced by C1 and produce another new store. Right? So in terms of valuation function, I can say that the valuation of C1 sequenced C2 or C1 semicolon C2 is a valuation of C1 composed with the valuation of C2. Right? So you can see in terms of composition, the order will get reversed because you go from left to right here. So that's the command composition that simply we'll have. Having said that, let us now take a more concrete example of a language. Right? So I'm putting it in the structure of the denotational format. Right? So the abstract syntax has these entities. Let's say P is a program, C is a command, that is a sequence of one or more program is a sequence of one or more commands. E is an expression which has a value. B is a special expression called the Boolean expression. I is an identifier, and N is a numeral. So we are restricting the language to natural number constants only, just to keep things simple, because that does not have any specific proliferation in terms of the denotational semantics of the commands. Right? So you can easily understand that these all will need to be defined. If not already defined, they will need to have their corresponding semantic algebra. But we are now just talking about the abstract syntax. So these are the symbols of the abstract syntax, and in terms of that, this is in Backus-Naur form. This is the kind of the grammar or syntax of the programming language. So we say P is, or program is, command period. The period means the termination of the. Then a command is sequencing of two commands, C1 semicolon C2, or it is if B, where B is a Boolean expression, then C, the conditional, with a dangling else, or it is a more complete conditional with if B then C1 else C2. You all understand the semantics, what is meant by this. Or I have an assignment where an identifier I is assigned the value of an expression, or I have diverge. Diverge is just kind of a synthetic command we are introducing here to represent all kinds of commands which may not terminate. So it could mean, so you can see what is missing here is a loop. So you cannot, in this language, there is no way for the control to go back to an earlier command, because there is no going back kind of command here. There's no loop also. So we will see what are the issues with that. We'll introduce that, but we include all of that in terms of a notion that there is a diverge command. So if you end up with a diverge command, then you are not being able to terminate, so you do not produce anything. Your store turns out to be a bottom. You have expressions, which is addition of two expressions. You can have a whole lot of unary, binary, ternary, all kinds of expressions, but we are just using one because the treatment of all of them will be very similar in the denotational semantics, and we have already seen what they would be. Or an expression is an identifier. An identifier by itself is called is considered to be an expression. It has a value, and or it is a numeral, that is, it's a given constant which has a value, right? So expression is something which has a value. Similarly, in terms of the Boolean expression, we are only considering the equality relationship just as a representative. And in terms of Boolean operation, we are just considering the negation operation. All others can be included in a similar manner, just keeping things simple. So diverge is a non-terminating command. This is the abstract syntax of the language that we are dealing with. Now, we need to define the semantic algebras for all of these. So we have truth values domain that we have already defined, TR, which is the Boolean. So true, false, and not is what we have given here, because that is what we need in terms of handling the truth values that we have allowed in the abstract syntax. We need a semantic algebra for identifiers. So domain is ID, which is identifier. So any identifier is an ID which belongs to this domain. Then there are natural numbers, which we have seen before, NAT, which is natural numbers, of course, with the exception that we had mentioned earlier, that it includes 0. So there are constants and two operations. One is plus, which we have seen in the abstract syntax of E, and one is equals, which we have seen in the abstract syntax of B, or the Boolean, right? So these are the two operations that we currently look at in the semantic algebra. Finally, we define a new semantic algebra for store. Now, store necessarily, if you see, store is a mapping of an ID to its value, right? That is what the memory is. You have an identifier and it has a value. Don't consider the complications of a store being physically represented in an electronic memory with address and all that. Just look at the mathematical way. The way we look at it at the program, we do not naturally, when we say x is assigned 3, we say x has a value 3. We don't consider, we are not trying to overload us with what is the address where x will exist, what value will be there in that x, in that address, which has to be 3, and there's a binding between x and the address. We are not getting into those complications. We are just looking at the highest abstraction level, that x is assigned 3 means x has a value 3, right? So store is a mapping between an identifier and a natural number, this value. Now, therefore, operations are, so if you look at it in that way, it is some kind of a generalized array you can think of, so it's kind of an indexing with the ID. So you can have a new store which gives you a store, and we assume that a new store is always initialized with zeros, right? So it is lambda I dot 0. So no matter what the ID is, its value is initialized to 0, right? So that's a simplifying assumption we are doing. It will become handy as we go forward. Otherwise, we'll have to handle the error or undefined store value and so on. Now, then we have an access that we can find out. Given an ID and a store, we can find out the value. So it is, so store, as I said, it's kind of a indexing function like the array. So it's lambda I, the ID, lambda S, the store. So SI is the function which finds out, given I, what is the value of I. Update is done in a similar way. You have an ID, the value that you want to update for that ID, and the store, and you get a new store. So it is lambda I, the ID, lambda N, the value, the NAT value that you want to update. Store is the current store, And we do this, modifying mapping that we had seen earlier, bar arrow, in, which says that in S, everything else remains same in the mapping of Si, except I maps to N now, right? So this gives you a new function, new Si function, which is the store here, right? So it gives you a new function. So this is the semantic algebra of the store. So we have now defined the semantic algebra required for our booleans, for our natural numbers, and for the store that is involved in terms of executing the commands. Right? So now let us try to define the valuation functions. So what is a valuation function for a program? What will you understand? And now naturally program needs to have some input, and it needs to produce some output. We are again making some simplifying assumption that the program will have a single natural number input, not multiple inputs and so on. All those can be handled, as you know, by extending these semantic algebras. But the minimum required is the program has an input, which is a natural number. So we say that the input number is n, and we say in the store it is associated with an identifier A in a new store. Right? Just a specific identifier A, let's say. And given that, I have the program, which is P, and I have this input N, which is associated with the identifier A in the new store. Everything else is new in that store. So everywhere else, for every other identifier, the value is 0. But for A, the value will be N. That is my input state. And now as it is evaluated by the valuation function, when it terminates, the answer is extracted from the store at the value at an identifier Z. It is pre-decided, right? Just to make things look simple. Right? So there is a location A where you get the input in terms of the program, which is set to N, and the result, whatever is produced when the program body is evaluated, that result is stored at a location Z, at an identifier Z, not location, identifier. It can be extracted from Z. And mind you, the program may not terminate. So it may not produce a result, it may not produce a Z. So therefore, you have a lifted domain for your result codomain. So it's not NAT, it is NAT lifted. So the lifted one, the bottom will be produced if the program does not terminate. So this is a simple look of any program in terms of the valuation. Now, what is a command? The command is, as I said, it's a transformative operation, transformative phrase from one state of the store to the next state of the store. So command takes a lifted store because already some command has executed on the store and you do not know whether that has terminated or not. It may have generated a bottom. So command, the valuation of command takes a command and a lifted store and produces a lifted store. So these are the different valuations. These are the different commands for which the valuation will have to be defined. So in terms of the sequencing clause, okay. Now, the first thing that we must note is the clauses of the C function, the C valuation function, are all strict in the use of the store. You remember there is two ways we can, once we have lifted a domain, there is two ways to do the valuation. One is in terms of strict, or one is in terms of non-strict. If it is non-strict, then before applying the lambda, we do not check if the input on which we are applying is bottom or not. We apply it irrespective of whatever is the input. But for a strict application, we check if the input is bottom. And if the input is bottom, irrespective of what the lambda is, the result will be bottom, right? So that is a strict application, lambda underscore, that we have seen earlier. So here, all clauses of C function are strict in their use of the store, quite obviously, because if I have a store which is bottom, which means that the previous command has not terminated. Obviously, since that has not terminated, the next command cannot even start. So the next command also semantically does not terminate, right? So you cannot apply the next command on the store which has not been produced because of non-termination. And therefore, the store that you get by applying this command is also a non-termination, right? So that's the kind of logic. So command composition, we have seen how it works. The conditional commands are choice function. We have introduced the choice function. So this choice function is non-strict in the argument of E1 and E2 and E3. For example, if we do if B then C on S, and when B is false, B on the evaluation of S is false, then the result of this computation will be S, even though the valuation of the inner C could be a bottom. Right? So if you had checked in strict, you will immediately produce a bottom because S is bottom. But if you don't, then in case of B being false, you actually never execute this true part. So you don't care if it is bottom or not. So if it is false, then you simply reproduce that S. Right? So that's the kind of logic. Assignment statement will perform an expected update. We know how to update the store. And diverge command will cause non-termination. So we can see that for all the commands, how we will go about writing the valuation function. Then the valuation function for the expressions. So expression will take the store and produce a value. What expression has? An expression always has a value. So expressions represented by E will have a NAT value. Expression represented by B will have a TR value, truth value. And natural numbers will N, the valuation N will map a numeral to a NAT. That we have seen this before. Now here you can see that the function E, the valuation of expression, also needs the store argument, right? Because it is in the context of the store, it's in the context of the data structure that you are evaluating the expression. The expression will have identifier. So that identifier has a value in the store. And you are evaluating the expression in the context of that value of the identifier. But the difference from the command is the store is used here just in the read-only mode. So you are just reading, finding out what is the value of the identifier to evaluate the expression, but you do not update anything. That is the reason, if I go back one slide to 11, that is the reason that your final result is not stored, not change in the store. It is just using the store to read the current value of whatever is required. But the final result is a value, right? So that's the difference with a command. So its functionality shows that an expression produces a number, not a new version of store. The store is not updated by an expression, right? That's the difference between a command and an expression. The equation for addition is stated so that the order of evaluation of E1, E2 is not important to the final result. So that's the assumption we are making, that if we are doing E1 plus E2, it is not specified as to whether I should evaluate E1 first or I should evaluate E2 first. I can do them in any order. In fact, they can be done in parallel also, right? So that's the interpretation we have. And this is quite logical because when does the order of evaluation between two expressions E1 and E2 become significant? It becomes significant only when they have side effects, right? In a standard programming language terms, that is evaluating E1 besides doing the value if it changes something else. Now, since in our formulation here, expressions are pure in the sense that they would never change the store is only read only, there cannot be a question of side effect. If there is no question of side effect, it is immaterial. The value of E1 or the evaluation of E1 will be the same whether it is done first and then E2 is done, or if E2 is done first and then E1 is done. None of them produce a side effect, so I can evaluate them in any order. The strictness check of the store is also not needed because expressions don't appear by themselves. Expressions are always part of a command. And the command has already checked for strictness. So a command will pass on to the evaluation of an expression only if the store is valid, right? If it has a result. So before actually it comes for the evaluation of expression E, the store validity of the store has already been checked. So strictness is not required for the valuation of the expressions, right? This is what these are the little bit of assumption and observations that we can make. So now we are ready to define the valuation functions. So first and probably the little bit most involved is the valuation function P of the program. So what it takes again? It takes the program and an input natural number, right? Which we say is n, right? So what did we say? That this input natural number will be updated at identifier A in the new store, right? So if n is, so this is the input natural number lambda n. So it will be updated on A. So update A and new store. New store, it's where for all identifier the value is 0. So this gives you the store with which P will start the valuation of C dot. So let us call this store as S. So let S is equal to this. So which gives that I start at a state of the store where my input n has been set as the value of identifier A. Right? And with this, what do you evaluate? You evaluate C. Right? So you use the valuation function for command on C in the context of this S. Right? So this is the valuation of the command. Right? And so this will produce a new store, right? Because every command is even a single command will change the state of the store. So you have a new store S prime. And in that store, we know that the result is assumed to be available as the value of the identifier Z. That was our assumption, right? So how do I get that value? So once I have done the valuation of the command C in the context of initial store S, I get a new store S primed. And from that S primed, I will access the value of Z. Right? So I will do this access. So whatever value I get from there as the value of Z in the new store is my result NAT. Right? And that could be a bottom. I may have non-termination. Right? So that is the simple way to express the semantics of the valuation of the program C dot. Right? Now let us go to the individual commands. So the command maps from a lifted store. The valuation of a command is in the context of a lifted store. So it takes a command and the lifted store and produces a lifted store. So in terms of sequencing, we know first it's a composition. So first C1, the valuation of C1 will be done with S within this bracket. So that produces a new store. And that new store will be used for the valuation of C2 to produce yet a new store. And this is a strict application so that it will check before doing a command valuation if the store is bottom or not, right? Rest will follow in the same manner. If B, then C. So a strict application of, you do the valuation of B in the context of the store. If it is true, you do the valuation of C in the context of the store. If it is false, you just return the store, right? So that's what you will get. Similarly, if B, then C1 else C2. Simple in terms of the choice function. Well, do the valuation of B, the Boolean condition. If it is true, do the valuation of C1. Otherwise, do the valuation of C2. Assignment. So we are assigning an expression to an identifier. So that will mean that it will change the store by creating a new association for the identifier I, which is the value of the expression E. So we do the valuation of E by the valuation function of E in the context of the current store to get a new value, right? E always produces a value, not a store. So this gives you a new value which you want to update. So you update takes the three parameters, the identifier, this is the value computed from the expression, and the store, and updates the association of I to this new value. Obviously, the valuation of diverge is bottom, right? As assumed, the diverge is all kind of non-terminating operations, right? So we have the valuation of the program P and the valuation of command C. Expressions are simpler. So expression is done, the valuation of expression is done in the context of store S to produce a NAT. So you do the valuation of E1 in the context of the store, do the valuation of E2 in the context of the store. We are not specifying in which order we do them. Then you have two NATs and you use the plus operation available in the semantic algebra of NAT to add them to get the final NAT value. And the application is non-strict, as we have already observed. The valuation of an identifier is accessing its value from the store. So you access IS. Valuation of a numeral is a numeral expression is a valuation of the numeral. So that's simple. Similarly, for Boolean expression in the context of the store will produce a truth value. For equality check, we'll do the valuation of E1 in the context of S, valuation of E2 in the context of S in any order, and then use the equals operation of the NAT, because these two are natural numbers, equals operation of the NAT to produce a truth value, which is the value that this Boolean expression will result. Similarly, for negation, we'll do the valuation of the Boolean expression in the context of the store and use the not operation of the truth value semantic algebra to get the new truth value here. Numerals are obvious, right? So this is what is the complete denotational semantics of the language. Before I get into the example, I will now work out an example. Let me just go back and check if you have any questions. Any questions, friends? No questions. Okay. So everything is understandable. Good. So it will become even clearer as we work through the example. Okay. So I'm back to the slide. Okay, so here is a program. The program is Z assigned 1 is the first command, followed by if A equals 0, then diverge, second command, and Z assign 3 is the third command. Then you have a period. So this is the whole program. The input to that is 2, right? The program needs to have an input, as you have seen. There's a value of n we had. So let us write this valuation function. So it has to update. N is 2. So update A with 2 in the new store. This is what you'll need to do to get a store. And then this whole program, the sequence of commands will have to be evaluated by C in the context of S to get a new store S primed. And then in S primed, we access the value of Z. Right? So this is what we will now try to evaluate. So let us look into this part, what we have, S prime and this. So what this S has become, so that is what I have written down here. So here you have S. So what S has become is it has done an update of A to 2 in the new store. So which means that in the new store, you have this modifying application, which is A becoming 2. Right? So let's focus on this command valuation. Command valuation, Z assign and all this. S1, I write this as S1, just, for, reduce the clutter, nothing else. So let us call this as S1. S1 is where A is 2, rest of it is new store. Right? I have a strict application here. This is the first command. And then the rest of it is the second command. So I evaluate the first command, which is Z assigned 1. Right? So this is what we will have, Z assigned 1 to be evaluated in the context of S1, and that store will be used in the evaluation of the rest. So let us just focus on this part now. So Z assigned 1 for S1. Because I'm having an assignment command, right? So Z will be updated with the valuation of the expression 1 in the context of S, and that value will be updated in S for S1. So I have S1 here as my starting store. So this is expression valuation of the expression 1, which is the valuation by numerals for expression for the constant 1, which is 1. Right? So this turns out to be 1. So I'm updating Z to 1 in S1. So what was S1? S1 was A maps to 2 in new store. So now I have Z maps to 1 and A maps to 2 in new store. So I have 2 updates and I called it S2. So S2 is a new store with A mapping to 2 and Z mapping to 1. That is what I get after the valuation of Z assigned 1 has been done. Now, in this context of S2, I have to do the rest. So that is what I write here. Right? So it is A assigned 0, then diverge. I'm sorry, A equal to 0, then diverge. So I will do Z assigned 3 with the result of the first command, again sequencing. So this will be done with S2. So I have the Boolean evaluation for A equals 0 in S2. And in S2, we know what it is 2, right? So A equals 0. A equals 0 is EA equals E0, right? The valuation of 2 expressions. So these are equals. So EA is accessing from S2 of A. Accessing of S2 of A is S2A, which is accessing on this store, and that is basically accessing A from, because it does not matter what the other values are, so I get 2. So I get here 2 equals 0, which is false. So if I go back, I will have a false here, which means I will get S2. Right? So this is false, implying that this is equal to S2. Right? So I evaluate Z assigned 3 on S2, which will, what will it do? In S2, it will map Z to 3 because it's an assignment. I'm doing a shortcut. 3 will have to be evaluated by expression E, then by valuation of E, then by valuation of N, and to get 3, I'm just shortcutting all that. So then I will have Z maps to 3 in S2. So this is Z map to 3 in S2 in access Z S prime. So after this mapping, whatever store will be, that Z is the accessing that Z from the store is the result, right? So it is accessing Z from Z maps to 3 in S2, which is Z maps to 3 in S2. You're trying to find out S, and you get 3. Right? A long way to derive. If I go back to the original program in 15 and use human intelligence, you will immediately say that A is 2. So Z assigned 1, Z gets 1, A is 2, so this is false, nothing happens, Z gets 3, so the result is 3. So all that we are showing here is this semantics, which is naturally what we get to see there, can now be completely mathematically derived through this denotational manner. Right. Let's change the input and see what happens in this program. So let us change the input, and let's say that instead of 2, I'm setting A to 0. So this is what we'll have, where S3, I'm again done a little bit of shortcut for this step. You have already seen the step. The A is mapped to 0 in the new store is S3. Right? So if I try to do this valuation, then S4, after having done Z assigned 1, maps Z to 1 in S3. So that is my S4, on which I will do the valuation of A equal to 0. And then we will have that. So that gives me diverge or valuation of diverge or S4, because if A equal to 0, then diverge. Right? Now this turns out to be true. Again, we can go through the steps, but as you can understand, going through the steps, this will turn out to be true. So this is C of diverge on S4. So which is strict lambda S of bottom on S4. So this becomes S4. This becomes bottom. So this now becomes bottom. Right? So if this becomes bottom, then obviously we can go on the sequencing again to use that to do the valuation of Z assigned 3. It's a strict application. So as store is already bottom, that application will also produce a bottom. Right? So now the final result of P is accessing, finding out the value of Z in S primed when S primed is a bottom. Right? That as we have already got. So naturally, if we try to do this, we will have a bottom because there is no termination. So the valuation of this program with input 0 is a bottom, which is also something which you can easily observe by human reasoning, that if A is 0, then Z is 1 is fine. A is 0, then is diverge. So it's a bottom. Right? So it's a simple, using a simple example with a language having assignment and conditional, we show that it is possible to do a very formal denotational semantics with the lambda calculus as the vehicle, and we get in a structured way. And as you can understand that this is not only structured, this is automatable. I mean, because all of these applications are mathematical applications, so they can be done by a program, and you can easily get that semantics evaluated. So let's, before we close, let's just take another simple example to show that there are cases when we might need to show that two different sequence of commands can actually give you the same store. For example, as you see here, x assigned 0, y assigned x plus 1. So what will happen? Whatever is s, after you do this, x will be 0 and y will be 1. This is another sequence which sets 1 to y and 0 to x. This will also have the same thing. I mean, intuitionally it is the same. So denotationally, let us try to prove that. So let us try to prove this. So this is what I have for the command. So I do the sequencing. So I have the valuation of x assigned 0 on s, which is x maps to 0. Use that for the valuation of y assigned x plus 1. So we can go through ex plus 1, all that. Naturally, ex will be 0 because we already have x as 0 in the store. So x plus 1, ex plus 1 will be evaluated to 1, with which you update y. So you get a store where y is 1 and x is 0 in the original store, whatever that original store was. That was S1. Similarly, you can do this the other command sequence. So first y assigned 1 will be done on S, y maps to 1. Then x assigned 0 will be done where x maps to 0. And you have another store S2. Right? So you have two stores now. Now, can you say if they are same? Right. Intuitively, yes. Mathematically, how do you say they are same? It's very simple. What you do is for every identifier, you try to access the value from both the stores. If for every identifier, the value accessed from both the stores are identical, then the stores are identical. The stores are the same. That's the basic logic. So are these the same store? So let's take argument x. So let's do s1x. So we will do an access on this. As we do access on this, we'll get 0. If we do on S2, again, we will get 0. I mean, naturally, I'm jumping steps, but you can write it in the proper access format. Similarly, for argument y, if I access on S1, I'll get 1. If I access on S2, I get 1. So, but if there is some other identifier that is other than x and y, then obviously that will have the same value as Si in both S1 and S2. Because S1 and S2 both have been done by updating S for X and for Y, and nothing else has been done. So for any other identifier, the values will be the same. So we can say that these two stores are same, implying thereby that these two programs are equivalent. These two programs, going back, these two programs are equivalent because we didn't make any assumption about S. Right? It is any store. Right? So this is a basic observation that we make for the languages. So we have just been able to take a look at the languages, imperative languages, the denotational semantics for that, and the imperative language with an assignment, and basic conditional. We have seen how to write the denotational semantics and how to do the evaluation with the with a certain store in the context. We will take this forward slowly, also look at programs as functions and then introducing file and other things. If there is any quick question, I can take that. Anything that was not clear in the presentation, I'll ask Shomen, we didn't upload this, right? This presentation?
No, sir.
Okay, okay. So I'll share with you. Just upload that so that you can also check and practice. And so, any question, friends? I don't know why attendance is low today. I mean, low in the sense of compared to typical. It's only 39. Anyway, it seems there is no question. So thank you then. Thank you very much. Have a nice day. And we will meet again on Wednesday. Bye.